All right, Isabella's going to come up here and talk to us about the perception of randomness in math and in life.
Awesome. I'm so happy to be here. Thanks to Thomas for the great introduction. Now I don't have to talk about the difference between Austria and Australia anymore. Happens way too often. Yeah, so I come from Vienna. That is what Thomas showed us on the map, the capital of Austria. I studied there statistics and psychology, therefore my topic. After graduated, I already worked as a volunteer 1 year in Berlin at the Anne Frank Zentrum, which deals with the Second World War. I worked as a social media analyst. I'm going to start a soccer statistics app soon. So it's been quite a detour to find my passion, and that is statistics, and I'd love to share that with you today. So my topic is the perception of randomness and order in life and in math. I want to merge together my two pieces of study, tell you the most interesting parts from here and there. I'm not an expert yet on all of those. I studied them a lot. I love it. But if you have any questions that I can't answer, I'll make sure to refer to the right sources. Plus, the library has brought out so awesome books. They're over there. They're awesome. So all the books I love are actually over there. Make sure you grab them afterwards before someone else does. So I want to introduce my talk with a short experiment I'd all like to do in your head. Maybe some of you know it. Just sit back and relax. I want you to think of a number between 1 and 10. Now, in your head. There's a pretty high chance that most of you chose number 7. Yeah, the laughs over there. Yeah, a lot of people did, I see here, yeah. That is actually very, very common. If we look at that chart over there, the 7 is way overrepresented. That experiment has been done over and over again. It works every single time, so if you want to really win a bet, that's a good chance. Yeah, so if you make people think of a random number, they'll most likely choose 7. And we can actually make use of that. I later going to tell you how to do tax fraud with the use of that. So, but first, how can we use the knowledge that humans suck at being random? We really do. That was just an example of it, but we could extend that. So, if we look at the lottery, I don't know how big your lottery is. In Austria, we have 45, I think it depends. How many numbers are included, you could actually extend that to a bigger set of numbers. And of course, you don't want to play those numbers, because other people might play them as well. So make sure to pick those numbers that no one else picks. You don't have to share your prize. Also, don't pick birth dates. They repeat, you don't want to share your prize. Also, don't use the numbers out of fortune cookies. You really think the Chinese people put a different number in any single fortune cookie? No, not gonna happen. And from a psychological point of view, and here it gets really interesting, I think, don't play certain lucky codes. What are lucky codes? Well, anything that is personalized just for you. That could be anything from, I don't know, your last zip code multiplied by your favorite color, like anything, literally anything. Because people are way more likely to bet more money on those kind of lucky codes, and therefore lose more money. So try to be random, even if it's hard. And from a statistical point of view, don't play the lottery at all. So I want to now tell you how to do tax fraud. Of course, disclaimer, I don't want to encourage anyone here in doing tax fraud. But if you do it right. So, I'd like you all to imagine that we own a little cafe in Austin, let's call it Bella's Nerd Cafe, and we have to send in the revenue numbers from every month to IRS from the last year. Of course, we don't want to really send in our real numbers because we want to keep a little bit of money to our own. I have here written out 52 numbers representing the revenue from the last year of our Bella's Nerd Coffee. Actually, of course, those numbers are not random, because I suck too at being random. So I took the liberty of actually taking the inhabitants of the 2nd to the 53rd biggest city in Austria. As we heard already from Thomas, yes, Austria is quite small. That, by the way, works because inhabitants and revenue have quite a similar distribution. So imagine the black numbers are our real income, our real revenue numbers, and I'd like to show some examples now in that very set of numbers. First of all, I altered them. I just, took a pen and scribbled something on the sheet, and that would be the numbers that we actually send into to the IRS. If we sum it up, we made about 2 million in profit, so pretty good. We altered it and sent in about 1.7, and there's a little bit of a difference that we just would not declare. So how, So how does the IRS now find out that we alter our numbers? By the way, those methods work for any kind of set of numbers if you want to find out if they're altered or not, but I thought that would be a really cool example. So there's basically 3 ways that you or the IRS can find out, some things is a little bit fishy here. We should better have a look at that. So the first thing is we look at the last digit. We will compare the last digit of the real numbers to the last digit of the fake numbers. We know humans suck at being random, and so do I. When we actually look at fake numbers, the last digit should have absolutely no distribution. It should be pretty much equal. However, we know already the 7 is way overrepresented. If we now have a look at my chart, we see I did a pretty good job at faking those numbers. The 7 even doesn't stick out. How does the IRS know actually that we faked the numbers? Well, there's a second way. We can also look at the first digit, at the leading digit. So again, we will compare the leading digit of the real numbers to the leading digit of the fake numbers. And here comes the bummer. Actually, the leading digit is not equally distributed anymore. If we quickly have a look at the numbers, the leading digits, we'll come back to that later, just to give you a little insight. We see, they're pretty much equal, but the 9 here, there's something weird. Keep that in mind. If I now tell you something, and I think that's awesome, there is actually a distribution that's called the Benford distribution to see how leading digits are distributed. There's a cool formula. I just wrote it down because it looks so awesome. I love it. It's awesome. And if you actually plug numbers into that, we'll get that distribution. And isn't that crazy? The 1 being the leading digit of any kind of big data set, that 52 is big enough in our case, is actually 30%. That's quite huge. I think it's hard to wrap your head around the fact that suddenly those numbers are not random anymore. That actually comes from the fact that the distribution behind such kind of numbers, revenue, or also inhabitants, has a certain kind of property, and that maps into here. By the way, how did I get that distribution? Well, I, of course, didn't do it, but there has been a guy named Benford, and I want to read that out because I think it's crazy. He looked at a big set of numbers that included the surface of 335 rivers, the size of 3,295 US populations, 104 physical constants, 1,800 molecular weights, 5,000 entries from a mathematical handbook, 308 numbers contained in the Reader's Digest, the street addresses of a couple of people, and also 418 death rates. So altogether, he looked at a quite variety of numbers, all in all about 20,000 sets of data, and he found exactly that distribution over there. So that is actually valid. And the IRS can now, or you, if you want to do it, can now actually have a look if the set of numbers that you have in front of you matches that very distribution. So we'll do that. I'll show you now a chart where in yellow you see the expected numbers as a leading digit from our set of numbers. And that is quite crazy. So if we look at the 1, I mean, and the first 2 bars are a little bit high, but what makes me sleep as a statistician at night is that they're still the most, so that's okay. But if you look at the 9, there's something off here. And that is exactly what should give you a hint to look better in your set of numbers. I mind you though, the Benford distribution does not tell you that those numbers have been altered whatsoever. However, it gives you a very, very close hint that you should have a better look at your numbers, because maybe something's a little bit fishy over here. And for once in math, that actually has a real-life application. And this is so awesome for me. This is like, that's awesome. So in 2009, in the presidential elections in Iran, election fraud has been discovered through this very process. Of course, again, they got a hint through that distribution to have a closer look in certain voting districts. In 2001, when Greece tried to get into the European Union, they faked their economic data. Yes, how do we know that? Well, Benford distribution, yeah. So actually, that's a really powerful tool to tell you more about your set of numbers. And I've already mentioned now 2 ways to have a look at your numbers to see if they're fake or how the IRS finds out that they're fake. The last digit, the leading digit, and the third one is outliers. Real women have curves, and real curves have outliers. If we look at our set of numbers, there have to be outlier. However, when we fake numbers, we tend to maybe take the very, very best days and make them mediocre. But then we lose an outlier. And real curves have to have outlier, otherwise they're not real anymore. So what do we do if we actually want to fake our numbers? Well, there's 2 ways. First of all, we can just take a set amount from every day and kind of shift our distribution a little bit downwards. Or second, we take the mediocre days, or even the bad days, and make them even worse, because then we have a more wide distribution and it looks more real. Well, now you know how to see if your numbers are fake, know how to fake your numbers better, whatever you want to do. Up to you, it's not up to me anymore. Yeah, so we see randomness is tough for us humans. However, it is also really, really hard for computers to be random. If we look at a number you think is random from your computer or your calculator or your Excel sheet, your R, SPSS, whatever you want to use, all those numbers are actually pseudo-random numbers. There is an algorithm behind all of them. This algorithm is way for us to crack. It's even way to us, all of us in our lifetimes combined to crack maybe. But possibly, potentially, some computers could crack your algorithm, which could cause a security hazard. So even computers can't do the random work for us. What a bummer. So what we actually could do, and this is awesome, like everything in the world, you can order random numbers over the internet. Not on Amazon Prime, though. So, yeah, that's a really missing thing. But what is actually happening is that there is a way to create really totally random numbers through nuclear decay. I'm not a physicist, but I'd like to imagine it that works somehow like that. Yeah, I'd like to imagine. Of course, hardly any university wants to have a teeny tiny nuclear power plant on the front desk. We're already so little students in statistics we can't lose anymore. So you can order all of those numbers over the internet to have your personal creme de la creme set of real random numbers. And that is quite cool, I think. So if you need any of those, there's a site called Hotbits where you can actually read up how it works. It doesn't work like that. It's hard for us humans to be random, but I'm sorry, order is not that easy either. I want to illustrate that on 2 examples. The first of all is that order depends on your view or your point of knowledge. I want to show you an example of an experiment where they put a mouse in one side of a box and a treat, I'd like to imagine it to be cheese, on the other side of a box. The only premise given by the scientist was that they have to pass at least 3 seconds from the mouse being over here to being over there. 3 seconds have to pass, nothing else. So what would happen? The mouse would be put in here, run over there, way too fast, no cheese. That would happen, maybe again, way too fast, no cheese. A couple of times it would go like that, and then something crazy happens. The mouse tries something else. I'd like to imagine it, that's a little zigzag, and then maybe a little roll. And suddenly the mouse was actually slow enough to get the cheese. And from that moment on, the mouse would do nothing else but the same zigzag roll over and over again. And mind you, the mouse could just sit over here, chill with some beer, having a great time, like we all do here today, and then just walk over and have the cheese, and it would be all right. But the mouse doesn't. And I'd like to have that as a little metaphor to kind of illustrate that actually we as humans have the possibility to do something else, unlike the mouse. And even if we don't get the cheese, we can still test out our surroundings. Another example is about the difficulty with order, is that order can change. It's not that easy, I told you. Imagine we're all in Saginaw, Michigan. I have no idea what that is, Michigan. So let's imagine we're all there. We don't know how it looks, but we're all there in our mind. About 7 years ago, we see someone in an orange uniform on the streets. We know that is an inmate, probably on the loose. We'll call 911 and he'll go back behind bars. There's an if clause in place. If orange uniform, therefore inmate. That works. Fast forward to 2014. Due to the big success, and that is a true story, of the Netflix series Orange is the New Black. Great 4th season, whoever's seen it, like awesome. Due to the big success of that series, the county jail chief, William Federspiel, has reintroduced the good old black and white stripy uniforms. Because he says it could potentially cause a security hazard, because fans of the show Orange is the New Black wear orange uniforms in appreciation of their show. Isn't that crazy? Just because of a Netflix series. Yeah, so he has reintroduced the good old white and black uniforms because the if clause, if orange uniform, therefore inmate, doesn't work anymore. I think that's quite crazy. All in all, we see that humans are quite caught in between. In between the randomness we really suck at and the order, that is quite difficult as well. It doesn't matter if we're a mouse in a box or a Saginaw, Michigan county jail sheriff. It's hard to deal with that, I think. I personally try to approach it from an analytics perspective. I study statistics, for God's sake. All I do the whole day is compute p-values and distributions, and not to forget our estimators, only to then tell you with a 95% possibility that that's random. That's my life. Okay, I try to overcome that in my personal life, however, with that kind of schedule. That is how my day looks, or how my week looks. I gotta say, the colors are not random here. There's order to them. That beautiful rainbow is a part of my 10 color codes. So that's true. Like, I've got 10 color codes for my life. It's actually not so many if you think about it. Yeah, so that is how I manage this hard time being in between the randomness we're suck at and the order that's so difficult. And I'd like to finish my talk with that story of mine. About 3 years ago, I was in a hostel in Berlin. I was watching soccer in the hostel bar, and there was this Northern Irish dude sitting over there. Well, and one thing led to another, and he's now a boyfriend of 3 years. We live together in Vienna. And some things in life are truly random, and that is quite soothing, isn't it? Thank you.
Several of your examples have to do with fraud. How do you plan to use this knowledge?
Well, there's no income tax in Texas, so I don't know.
We got you beat. All right, heavy question. Do you feel that, philosophically, humans are capable of true randomness?
I don't think so, because there's so many things constantly around us that we can't control, that we most likely even aren't aware of. So I don't think so, no. And that's kind of scary, but also not at the same time for me.
I want to remind folks that Twitter is available for your comments, but I'll also take hands from the audience, such as this gentleman.
How are you so sure of that?
How are you so sure of that non-randomness?
Well, I could randomly be random, that's true, yeah. Yeah, that's true.
Yes, sir. The Kansas gubernatorial election. So there was a statistician in Kansas that alleged gubernatorial election fraud based on these concepts. Were you aware?
I'm not aware of the Kansas case. I'd like to hear more about it, but what I can say is what has been discovered in Iran. Maybe that helps you. What they did is actually take district votes, and unlike the US, there are more than 2 parties involved. That leads to the fact that, yeah, it's crazy for Europeans. That leads to the fact that actually the district votes have been divided among several people, and therefore the Benford distribution works again. So that's how they did it there. Another possibility is what they can do is if they found irregularities in some kind of districts, they can compare those ones to the rest of the votes that are actually in place and in order that have been monitored. And if there's quite a big difference between those 2 parts, that's a big no-no sign for us. For example, I don't know if that's very controversial. I'm gonna say it anyway. If you use voting machines, of course that's way easier, and if you compare the votes by voting machines to the paper ones, you can find quite big off bits.
Yes, sir.
In your personal life, have you attempted to use random certain numbers again to order what you're going to do next?
Have you ever used randomness to decide what you're going to do next?
I don't know, just closing my eyes and reaching into the fridge doesn't count, I guess.
I used to take walks in high school where I decide what the stoplights would decide where I walked, and I just ended up walking in circles. Yes, sir.
So if you could order random numbers, what would researchers use those random numbers they ordered for?
An example is if you have a voucher code for something. Of course, if I have, I don't know, 5 voucher codes bought from Amazon, Amazon doesn't want me to be able to predict their algorithm to actually have voucher codes. So that would be one application of that. Is that clear? Okay, so if I see 5 numbers, Amazon doesn't want me to be able to predict the 6th number, because that would also be a voucher that I didn't pay for. So possibly, I don't know personally, they use totally random numbers as their voucher codes so that no one who has a good bit of vouchers sitting at home can predict the algorithm behind it. Is that okay? Okay, thanks.
Any comments from those of us in the audience who've worked on the Tor project? No? Okay. Yes, sir. Yes, sir.
In many ways, religion is man's way of dealing with creating a sense of meaning and order in a chaotic universe.
Whoa.
Does your understanding of randomness and order affect your religious beliefs?
Do you believe in God?
That's a good question. That really is. I'd like to answer that with the words of my biology teacher, if that's okay, because it really represents my feelings. She's also not only my biology teacher, but also my religion teacher. She was in high school, which is kind of a cool combo, I think. And she says, well, we had the Big Bang, and from there we had so much life created, but how does it come to that? That's so extremely random, but maybe there was a greater force actually involved in all of that happening, and all of those molecules and elements to be in the right place at the right time.
Thank you, Isabella. Any other questions? Yeah, sorry, Matt.
Didn't Einstein say that God doesn't roll dice? Right? Isn't that what they say?
Didn't Einstein say that God doesn't roll dice? Didn't he take that back at some point?
My real question is, can you explain in the Benford formula what the D was?
The D in the Benford formula, do you know?
basically, you could use the Benford distribution on any kind of data. Here, in our case, I would use the numbers from 1 to 9 to plug in as the D to then get percentages from it. Yeah, the D would be the set of numbers from 0 to 9 in this case, from 1 to 9 in this case.
Yes, sir.
If I go to a different number system, let's say binary, would that distribution also hold?
Do the Benford distributions hold in different numbering systems like binary?
I haven't done that research yet. That's a great question. But as the Benford distribution does tell you a lot about numbers from 1 to 9 as a leading digit, and the leading number a leading digit can only be 1 or 0, I think you might have to adapt it. But it could possibly work. Also, in larger systems, I would say that there could be an application for it, but there's something you should definitely look into. That's really cool.
Time for one last question. Yes, sir. Sorry.
So, Brian Greene, relatively famous physicist, doesn't truly believe in an infinite universe, doesn't believe it can be infinitely large, because at some point he believes that everything has to be set. So if you're going to have an infinite size or an infinite data set, at some point everything has to repeat, and you're reduced to believe that, like, there's a group of people somewhere else 10 trillion light years away, sitting in the exact same room having the same conversation, because of an infinite data set, you would have to have that happen. So do you think that there's like in an infinitely large data set, like, do you think there is any actual randomness, or does like entropy I guess you know, you get the question. Okay.
Can you repeat the question?
What does it even mean, man? If you have an infinitely large data set, what's the point of randomness? What does it even, does it exist?
Yeah, so what we as statistician or mathematic people always work is infinite large data sets. Doesn't exist, but we'll work with it. That's fine. And the question was, if we have an infinite large data set, if then things can possibly repeat. And if there's true randomness, if I got that right. Yeah, patterns. That is a very tough question, but like really, I would say that they could possibly repeat, but where and when is still random. So I personally, that is my personal opinion, think that even if there are some kind of repetitions, they are still within a random place. But I think that is actually more a philosophical questions if you believe in different worlds, like Sheldon Cooper. I think that goes beyond my knowledge, but I'd love to talk to you afterwards to actually discuss that, because it's something super important. It is in math, a little bit. So yeah, I think that if that's okay with you, then I'll leave it to that.
In an infinitely large data set, Chewbacca exists, so I think there's like more important questions. Yes, sir. Last question.
Do you believe personally that there is a mechanic of the universe that is truly non-deterministic, and if that could be included in some of the biology of learning in some way, not consciously?
It's a humdinger. All right. So, if there is randomness in the universe, might that universe be represented in some way in our own brains, our own bodies, that would allow for the randomness that you previously claimed is not possible?
I'm 21, and I'd love to give you my card. Call me up in 10 years, and then I think I'd be more qualified to answer that. Thank you.
Thank you, Isabella.